Welcome to webinar. I'm Anil Kumar. I'm a technical product manager at Couchbase. We will start with a brief introduction to Couchbase. Then we'll take a look at Couchbase architecture, its components, and also some of the basic operations today. So Couchbase is a NoSQL document database for interactive web applications. And with the Couchbase 2.0 release, it was a very big milestone for us, and it transformed Couchbase from a key value store to a document database. So we support both the binary data and as well as the JSON document in Couchbase. So now you can do a lot more with your data. You can index it, query it, and you can use cross datacenter replication to replicate your data to another cluster. Also, you have ability to do real-time analytics with the incremental map reduce functions and much more. So we will cover bunch of stuff in today's presentation. To just give you a background, Couchbase product itself is backed by Couchbase open source project, which is one of the leading NoSQL database projects, which is focused on building distributed database technology as well as the ecosystem around it. Couchbase supports both the key value use cases and as well as the document-oriented use cases. All the components of the Couchbase project, including SDKs, Couchbase Server, are all completely open source, which are available under Apache 2.0 public license. Now, in terms of packaged software, you can download Couchbase from our website, and we have both the enterprise and community editions available. So now let's look at some of the key functionality and the characteristics that Couchbase provides. First one is easy scalability. This allows you to grow your cluster without affecting your application. What that means is you can add multiple nodes, or you can scale up or scale down. You can remove some nodes from the cluster with just a click of button and no changes to your application. I'll be demoing this later in our session once we go through the demo session. Consistent high performance feature gives your application sub-millisecond response time, both for the read as well as write operations in terms of latency perspective. And this becomes very important in terms of user experience. This means that your end users will have a great app experience. In addition to the low latency, we also support consistent high throughput, and this is on a per node basis. So always on 24 by 365 feature gives you ability to never take your database offline. So if you are doing a maintenance operation, let's say you are doing a software upgrade, you're upgrading to the latest version of Couchbase Server, or if you're doing the hardware upgrade, maybe you're adding more RAM to your server, or maybe you're refreshing your hardware, or any maintenance operation, any applying security patches to your OS. These are all online operations in Couchbase. We have online rebalancing and online rolling upgrades, which will allow you to perform all these maintenance operations online. And we would demo this later in the demo session. So, and finally, we have a flexible data model feature, which gives a lot more flexibility in terms of building your application without a fixed schema. So now let's look at what's new in 2.0. As I mentioned, the 2.0 release for Couchbase was a big milestone. It was a major release for us. So with that, we added a lot of great new features in 2.0. We now support JSON document in Couchbase, which means you can natively work with JSON document in Couchbase. And that also includes editing the document, managing it, and also we have updated all our APIs and SDKs with new features which now have native access to JSON. Now with JSON support, we have ability to do indexing and querying in Couchbase. You can create materialized views over your data, and you can run queries in views. So basically, from your application, you can run queries to the the views you have created, which will be much across your data set. So we will demonstrate that later. We also provide incremental map reduce. With this feature, you can do real-time analytics on top of your data. So, for example, if you want to find a top contributor across all your data, so you can create a map and reduce function to do that, and we will show that. We'll demonstrate in one of the lab sessions. So, and finally, another big feature we added in 2.0 is a cross data center replication. This is a great feature because you can now replicate your data from one cluster to the another cluster. You can have the capability of data locality, which is bringing data closer to your user, and we will again demonstrate it in the demo. So let's now take a closer look at the flexible data model. In this example, we have a document with the user profile data. So we have ID, first name, last name, zip, city and state for this user, Dipti Bokar. So in Couchbase, you can have documents with a different structure. So for example, the next document can have the other user profile information with additional attributes. Let's say the other user might have the email address in the document. So what this means is we support having different structure or different schema of documents in the same database. So we call, in Couchbase, we call it as a bucket. Bucket is identical to database in the relational world. So when you make changes to the document, for example, if you add new attributes to the document, you don't have to bring down the database for any schema changes, because this all can be done with the JSON and it doesn't affect your application. With this, you get a lot of flexibility in terms of building your application or to make changes or push out the changes much faster without expensive like the alter table operation that might have been needed in relational world. So your application becomes much more agile. So you can make changes and push the changes much faster. So now let's look at the Couchbase architecture. So one important thing to mention here is, as I mentioned earlier, so Couchbase all the nodes in a Couchbase are identical. So if you, here is an example of Couchbase, one single node of a Couchbase. So all nodes are broken down into two components. So we have a data manager on the left and a cluster manager. So the data manager, it's important to realize that these are separate process within the system, specifically designed so that node can continue serving its data even in the face of cluster problems like network disruption. The data manager it's written in C and C++, and it's responsible both for object caching layer, persistent layer, and query engine. And it is completely compatible with Memcached protocol. So those who are familiar with the Memcached, there's one big difference is we have completely rewritten the data layer in C and C++ in lower level language to make it much more efficient and performant. The data manager also so it's completely compatible with Memcached protocols, which means we are not only drop-in replacement but also inherit and support for atomic item expiration, atomic incrementer, and bunch of other features from Memcached. Another important thing to note is all the metadata for the documents and their keys are kept in RAM at all times. Well, this does add a bit of overhead per item. It also allows for extremely fast MIS speeds, which are critical to the operation of some applications, so that we don't have to scan a disk to know that we don't have some data. The next, a cluster manager is written in Erlang language. This component is completely responsible for cluster level activities. It's responsible for the configuration, administration, process monitoring, statistics gathering, and UI and REST interface. So let's first start out looking at the operation within the single node. So as I mentioned, keep in mind that again each node is completely independent from one another when it comes to taking in and serving the data. Every operation is only between a single application server and a single Couchbase node. All operations are atomic and there is no blocking or locking done by the database itself. So in this case, let's see how the write operation works in Couchbase. So the app server tries to write this document 1 to the Couchbase server. It does a set operation. The document 1 gets returned to the managed cache. So once the document is in managed cache, we write asynchronously to the replication queue and a disk write queue. So the document on the replication queue is for the high availability. If you have configured replicas for your database, in case if the server goes down, we have another server to take the traffic. In that case, we have this replication queue, which is memory to memory, in a sense RAM to RAM from one node to another node. The document 1 in the replication queue will be sent to the another node, whereas the disk write queue will persist the document to the disk asynchronously. So this is how the write operation works in Couchbase. So now let's look at how the update operation happens. So let's, in this example, let's say that there was an update to the document 1. So the app server does the set operation again, and the document 1 in managed cache, it overwrites the document. So if the document 1 already existed before, it overwrites it. And again, for the high availability, it writes to the replication queue, and to the persistence, for the long persistence, you write to the disk write queue. In case of storing it to the disk, the mechanism we use is append only. So what that means is any mutation or any update to the document, we create entirely new document and it gets appended to the end. So the old document, which is a stale document, now it's old, that gets garbage collected when the compaction operation runs. So let's look at how the read operation happens. So app server sends a get request to the Couchbase server. In this case, the document 1, so and the document 1 is already in the managed cache, so Couchbase server immediately sends back to the app server. So let's now look at when your app server becomes, let's say that your app becomes viral and you start writing a lot of data to the Couchbase server. So as you start writing a lot of documents to the Couchbase server, there will be not enough space in the memory to hold new documents, new data. So in that case, we have a algorithm which we use to check the access log to find which documents have been not recently used, and even however we know that these documents are already stored in the disk, we evict some of the older documents. So in that way, we make room for the new documents to come in. So should we have a case where some of the documents are not in the already are rejected to the disk and we don't have it in the managed cache? So if the request come for such documents, in this case the document 1 that was not in the managed cache, we fetch it from the disk and send it back to the app server. So this is how the cache miss happens, and usually when reading from the disk, it will add some latency. So it's better to size your RAM properly so that we can accommodate all your active data set in the memory, so that we have a sub-millisecond response time. So now, understanding those same operations, let's look at how this functions across a cluster. With Couchbase server cluster of 3 nodes, you can see that documents are evenly distributed throughout the cluster. Additionally, the replica documents are also evenly distributed so that no replica document is on same node as it's active. After the application server comes online, so let's say that we have two app servers, app server 1 and app server 2. We have the client libraries installed on them. So these are called smart SDKs. The reason we call them as smart SDKs are because they have the information about the cluster map. So they have the partition map included in the client library. After the application server comes online and receives the partition map, all requests to the given document. So in this case, let's say the app server, they know that the document 5 exists in server 1. So all the requests, the read, write, and update requests will go from now on to the server 1 for the document 5. In this way, the Couchbase ensures immediate and strong consistency. An application will always read and write from the active partitions. So at no point is the replica data will be read, and which will cause inconsistency. So we will see later what happens when a node fails and how we promote the replica data into the active state. So in terms of how we have distributed the data across the server, we use a hashing algorithm to evenly distribute the data, evenly and randomly distribute the data across all the nodes. By distributing the data evenly across the cluster and letting the client load balance themselves, the load also evenly distribute across all the nodes in the cluster. So if we have 5 servers and if we have 3 servers in the cluster, all the 3 servers will be taking the same load, equal even load. And we will and when I show you the monitoring system in Couchbase, I will demonstrate how the load is distributed across the servers. So one quick thing to mention here is, although the diagram only shows a few partitions of the data, we actually use 1024 logical partitions. We call them as V buckets in Couchbase. So we have fixed number of partitions we create across the cluster. Now let's look at what happens when it comes to add servers to the cluster. So as I mentioned, if your application server needs more capacity, and if you want to increase the capacity in the server, so you can add more servers to the cluster. So let's take the same example. We have 3 nodes in the cluster. Note that you can add or remove multiple nodes at the same time before actually migrating any data. So let's say in this case we have added 2 nodes at the same time. This helps greatly. This is because when you need to add or swap lots of nodes, you don't have to move the data around multiple times. Once the administrator is ready, pressing the rebalance button, it's very simple, and I'll demonstrate it later. The data some of the data from this existing servers will start migrating to the new server. So when the rebalance button is clicked, as you saw, some of the active partitions as well as replica partitions moved from the existing server to the new servers. Despite what the animation shows, this is actually done incrementally, one partition at a time, which means that load is immediately and incrementally moved to the transport to the new nodes. So as the partition starts moving to the new nodes, they become available for taking traffic. The cluster maps will get updated from the client library, and it knows that the partition has, in this case, let's take an example, the document 9, which was earlier in the server 1, has now moved to the server 4. So the cluster map gets updated in the client library, so they know the document 9 doesn't exist anymore in the server 1. It's moved to the server 4. So any request for the document 9 or document 6 will start moving to those new servers. The same process can be also used for software upgrades, hardware refreshes, and removing or swapping out misbehaving nodes. Finally, let's look at what happens when a node fails down. In any system, it's very unfortunate that some of the servers will go down, and in such situation, let's see how Couchbase reacts. Imagine the application is reading and writing to the server 3. In reality, it's sending requests to all the servers, but let's just focus on server 3. If that node goes down, there have to be some request that fails. Application server will start getting the timeouts. Once the failure is detected, the node can be failed over either automatically by the cluster or manually by the administrator, pressing a button or a script triggering out the REST API. You can basically configure the automatic failover in your admin UI. You can set the timeout to 30 seconds in this case. So if the clients are trying to reach to the server and if they don't hear anything back from that server for 30 seconds, it will automatically fail over to the other servers. In this case, now that we have identified the server 3 it's down, we activate the replica partitions on the other nodes. So as you saw that some of the replica partitions on the other nodes got promoted to the active, and they will start taking traffic. So the cluster map on the client library gets updated. So they know that the server 3 is down and the replica partitions on the other servers are active now. So and another important thing to watch here is the replica partitions are on the other servers are evenly distributed. So not one server will take all the load. It's not it's proportionate. It's all the other servers will take the load, and it's a good idea to when we for example, if your fail node can be rebooted or replaced and rebalanced back into the cluster. It's a best practice to return the cluster to full capacity before rebalancing, which will automatically recreate any missing replicas. Okay. Now that we have walked through the Couchbase operations, let's see how easy it is to scale your Couchbase cluster. So before we start, just wanted to show you that if you can install the Couchbase package from our website. If you go to couchbase.com/download, you can see all the binaries for different platforms. We have binaries in both the enterprise edition and community edition. So to walk you through when you install the Couchbase on your machine, to walk you through the setup process. So I have set up a right-scale template. So we have right-scale template, which is basically you can use that for bringing up the AWS EC2 instance. For the demo purpose, I'm using those right-scale templates. Yeah, so we have some right-scale templates for the different versions. So I'm using the right-scale template for Couchbase version 201 to demonstrate. So once you install the Couchbase, so I'll walk you through the setup process. So once you install, you go to the localhost 8091 port, and it will bring up the setup wizard. The first screen we'll see is the configure server. In the configure server, you're configuring the settings for the whole cluster. So you can set the database path, you can set the index path, and it's ideally best practice to separate the database path from the index path for good performance. And also you can add, if you have already a cluster, you can join to the new cluster into that existing cluster, and I'll demonstrate this later. So now let's go to the next screen. So also part of the installation, we provide the sample buckets, so we can play around with the Couchbase. We have a BS sample and game sim sample. You can checkbox and you can install those samples on your Couchbase. The next thing we do this setting is the default bucket. As I mentioned before, the bucket is identical to database in relational world. So we have a bucket settings. So as I mentioned, the default bucket we create is the default. We have an option, a bucket type. We have two options for Couchbase. We have Couchbase and memcached. If you select memcached, it will be all in memory and there will be no persistence. Whereas if you select the Couchbase, it provides both the in memory as well as the persistence layer. And also we can set the memory size, the RAM quota for the bucket, and also as I mentioned, if you want to configure replica for your database, you can create up to 3 replicas for your database. Within a cluster, we support having up to 3 replicas. And finally, the flush option is for only development mode. When you enable this flush option, the developers, whoever is working on the Couchbase, can use this option to delete clean away all the data from the bucket. And this we recommend this to be disabled. And again, so if you want to get updated with the latest updates on the Couchbase, you can register here, and we usually send the notifications out on the new Couchbase Server version and all those stuff. So finally, you have to provide the username and password. So once you do that, so this is a single node of a Couchbase. So we have this page, and I have already set up a 3-node cluster to demonstrate. So here in this one, for the demo, I'm going to kick off some load to show you the live traffic. Okay. So let me walk you through the admin UI. So this is the front page. When we arrive to the Couchbase, it comes to the cluster overview page, which basically gives you the snapshot of the complete cluster. So it has information on the bucket. You can get the information of what's the operations per second or disk fetch per second. How many servers are installed in the cluster, which server is down, like how many servers are down, or if they have failed over, or any pending rebalance. So we get a snapshot of the whole cluster on this page. When we click on the server nodes page, this lists down all the servers in the cluster. So in this example, in here we have 3 nodes already part of the cluster. So the status is up. It means that they are active, and there's few other stats here, and also we have failover button and the remove button. So let's say that this server starts misbehaving. We can use the failover to remove it from the cluster, and the other servers will take the replica partitions on the other servers will start taking the traffic. So we will demonstrate this stuff in later. So let's go to the data buckets page. The data buckets, as I mentioned, it's the bucket is equivalent to the database. Here, by default, we create the default bucket. So once you start creating the documents, if you have not set up a new bucket, all the documents will be stored in the default bucket. Buckets are for application specific. So for example, if you are building a new application, you can create a new bucket for that specific application and start storing the documents for that application. So when you expand the default bucket, you can get some additional information, such as how many replicas have been set, if the compaction is enabled, and also what RAM quota we have configured, and what's the storage size. Similarly, if we go back to server nodes, we can expand the server, one of the server, and see additional details. So we can see what's the server name, how long it's been uptime, what's the OS version, what's the version of the Couchbase server installed on this machine, and again, what's the usage in terms of RAM and disk. So let me show you the operation of adding new servers to the cluster, and I'll demonstrate how easy it is to add new servers to the cluster. So I'll utilize the same machine which I just set up. I can take the IP address. So on this screen, you click on the add server, provide the IP address, So if this server already has some data, when we make this as part of the cluster, part of our cluster, it will automatically wipe away all the old data from there. So we have to be careful that if you have a node which has some important data, make sure that it's backed up and you're not mistakenly adding any server like that. So when you click on the add server, you can see that the server got added. It's in the pending rebalance state. So let me add another server. Yeah, now you can see that we have two servers which are added, which are in the pending rebalance state. So they will be marked as pending add. What this means is like you can add multiple servers, keep them ready, and when you want to add, make them active. When you want to start moving the data from these servers to the new servers, you can hit the rebalance button. So when everything is ready, you can click the rebalance button. You can see that these new servers have they are added. They are still in pending state. As the single partition starts moving to the server, they will be marked as active because clients can see it now and they can start talking to the server. So the rebalance is still happening. Well, this is still happening. I can show you the stats. So for example, we have vBucket resource. We collect bunch of, we have almost 200 plus stats we collect from the cluster. So in this case, let's click on the vBuckets. So we have, as I said, we have 1024 vBuckets. You can see that some of the, so these were the 3 nodes which were there before. Some of the partitions from these servers are getting transferred out. So you see that the numbers are decreasing here, and as well as on the new servers where the partitions are moving in. So in a sense, like as you see, they keep increasing. So this will go on till it evenly distributes the partitions across all the servers. Yeah. So once the rebalance operation is complete, they will all have the same number of vBucket partitions on the servers. So one important thing to watch here is when this whole operation is happening, your application is still able to read and write, and there's no effect to the application. They can till the partition completely get transferred to the new servers, the application will be still talking to the old server. There is a switch over which happens, and when the switch over happens, that's when it start talking to the new server. So as I mentioned, we collect bunch of stats here. So let me show you. This is across the cluster. So when you click on the operations per second, it shows you we have almost around 6K to 10K ops per second happening on this cluster. But if you want to see ops per second on the server, so you can click on show by server, which will show you that the ops per second per server. So when you click on this server, it will show that on this server what's the ops per second happening, and you can see that it's consistent across all the servers. So let's switch back to the old view. Also, we have other stats such as cache mesh. We have the gets per second, sets per second, and a bunch of other stats which are very important for monitoring your system. And also, we can filter this data based on a minute base, or on hour, or day, and weeks. So you can change these settings and see the graph, and we can get more details on these stats. Okay. So now let's go back to the presentation. Before that, we can open the floor for a few questions now.
Okay, that's great. As a reminder for folks, if you have a question, you can just type it into the GoToWebinar panel, and we'll be sure to address all the questions that we can. We have one question from Perry about size of the server nodes. So he asks, how large should the server nodes be, especially when talking about the RAM size?
So we have a good blog to talk about how to size your cluster. So basically, it depends upon your workload. So depending upon the workload, you can we have a sizing calculator which you can use. You can input few things about your cluster, about your workload. It will calculate and let you know that what RAM capacity, based on what RAM capacity, how many servers you would need, or what would be the ideal RAM capacity for your cluster.
That's great. Thanks, Anil. We have another question about the rebalancing process that you just showed from Paul. He asks, is rebalancing an image transfer process, or does the time depend directly on the amount of data that's being replicated?
The time depends. Actually, that's correct. So time depends upon the data being transferred. It's not actually the image. It's more. We use a TAP protocol, which is a protocol for transferring the data, which does it in a bulk operation, and it's per partition based. So, for example, if you have 10 partitions which are moving from the server 1 to the new server, it will start with the first partition. It does the bulk operation to do the data transfer. Once the data transfer is complete and the new partition on the new server is in sync, it will switch over and it marks it as a active so that the clients can start talking to it.
That's great. Okay, we have time for one more question. What APIs are exposed for monitoring and data collection, or is the GUI the best way to obtain information about the cluster?
All the stats I showed here, everything is available as a REST API, so most of the stuff are well documented, and we have and if you go to our website, you can see the documentation. So, but the point is, all the stats we collect, I mean the APIs here are all available as a REST API.
That's great. Thanks, Sunil. Okay, at this time, feel free to continue the presentation.
Okay. Thanks, Baxter. So let's get back to the presentation and take a look at how the indexing and querying works in Couchbase. So as I mentioned before in the earlier slide, with the JSON support, now we can create materialized views over your JSON documents. And your application can use this view to query the data across the data set. Using views, you can define primary, secondary, or more complex indexes, and you can, in fact, we have inbuilt aggregation functions. We provide count, sum, min, max, and these are inbuilt and which are much optimized. You can use it for reduce functions, and I'll demo this in the example later. So we do so indexes themselves are eventually indexed, which means that there is slight delay between when the data is available on the disk and the indexes are updated. And also the queries are eventually consistent by default. However, the developer have an option to use a API. We have a special API called Observe, which developers can use for making sure that the queries for the indexes are also strongly consistent. The function itself, the views, the whole function itself is written in JavaScript, and we'll take a look at the examples in a bit. So let's see how the indexing works on a single node. So going back to the earlier example, so we have the app server which writes the document to the managed cache. It gets it's sent to the replication queue and the disk queue. Only when the document gets persisted to the disk, it becomes available for the indexing. So it gets once it gets persisted to the disk, it gets picked up by the view engine, and the index gets updated. So as you saw that the document doc1 now it's part of the it's got updated as in the index. So any queries, so because there is a delay between writing it to the managed cache and then writing to the disk queue and the disk, the queries are eventually consistent. So yeah, now let's see how it works across the cluster. We have indexing and querying capability which are cluster wide. When we first create an index on a cluster, it will create that data structure on a active data, which is a subset of the data on that server. For in this example, we have 3 servers, and they each of them have the subset of the data. So index will be created on those subset of the data. So which and also you can optionally create replica index as well, so that you can, when you fail over the server, let's say when one of the server goes down, you don't have to rebuild the index all over again for those partitions. Now let's take a look how the query side of it works. When a client needs to query the data, given that queries needs to be executed across the entire cluster, because we don't know where exactly the data is in, so it has to be executed across the cluster. The client randomly selects the server from the cluster and sends the request. In this example, let's say the app server 2 sends the request to the server 2. In this case, the server 2 will act as a coordinator or orchestrator, and it uses a mechanism called scatter and gather to send the request to the other servers and get the results back and send it back to the client. So here, as you saw, the request was sent to the server 2. It sent the request to the other servers, got the result back, and sent it back to the app server. So now let's look at the another big feature we added in 2.0, which is cross data center replication. We call it as we have a short acronym for it. It's called XDCR. The XDCR gives the ability to replicate the data from entire cluster, from one entire cluster to the another cluster. The cluster can be spread across different geos. So replication can be configured on a per bucket basis, which is like per database basis. So, for example, if you have different buckets in the same cluster, you can choose which database to replicate and which database not to replicate. Also, we support both the unidirectional and bidirectional replication, which means that you can have active replication streams. So I will demonstrate this creating the unidirectional and bidirectional replication in the demo in a bit. So that when we create a bidirectional replication, you can have read and write that happens on the source cluster in the data center 1, and also you can have a read and write that happens on the data center 2 as well. By default, we have 32 replication streams set up on the node. So this is configurable. You can, if based on number of based on your server capacity, you can increase the replication streams. One thing to mention here is this cross data center replication is different from the intra-cluster replication, because intra-cluster replication works ramped from memory to memory, whereas the cross data center replication works from when it gets persisted at disk. Here is an example. So in this example, we have the cross data center replication flow on the single node. The same operation, the document gets written to the managed cache, and it gets sent to the replication queue. This queue is for the intra-cluster replication, which is for high availability. When the document 1 gets persisted at the disk, that's when the document gets sent to the XDCR queue, which will then be sent to the another cluster for disaster recovery or for the data locality. So let's take a look at the use case where we have an existing data center, which is in New York data center, which has 3 nodes in a cluster. And now let's say that we have growing number of users in the west side, and we want to set up a San Francisco-based data center. So for simplicity, let's say that we have the same nodes on the destination cluster, but it need not be. It can have it can be arbitrary number. For example, on the source cluster, we might have 5 nodes. On the destination cluster, we might have only 2 nodes or 3 nodes. And we support that completely, because we create the partition map based on the cluster. So even if we have arbitrary number of nodes, it's still supported. So when we set up the XDCR replication, it creates 32 replication streams from the source cluster to the destination cluster per node. If there is a topology change, for example, if you want to scale up or scale down nodes in the destination cluster or the source cluster, the XDCR is a topology aware. That means it will get updated with the new map, and it will know where exactly the partitions are moved. And when the replication streams, it will get updated. It will start transferring the data to the new location of the data of the partition. In case of bidirectional, the way it works is, let's say that you want to make the both cluster active. We can set up unidirectional replication back from San Francisco data center to the New York data center. In that case, we have two unidirectional replications, one from the New York data center to the San Francisco data center, and the other one from in the reverse order. In this case, we have active clusters. We have bidirectional replication going on between them. So the obvious question would be, how do we handle the conflict in that case? So let's say in case of a conflict, that is, if the same documents get updated on both sides, we have a mechanism which we use. We call it as a based on number of mutations that has performed on a document. We find the winner. But if there is a tie in that one, we use other flags. We have revision ID. Which is basically a cache value that is a unique timestamp to break the tie. Even if we don't have, even if we still have the tie, we have other stuff to break the tie, like the sequence number and the other flags. Okay. So we also have an Elasticsearch integration. This is for the full text search. Underlying, we use the same XDCR protocol protocol for transferring the data from the Couchbase cluster to the Elasticsearch cluster. So we have a plugin which is built for, and it will be in the Elasticsearch cluster, which knows any mutation which are happening on the document will be sent over from the Couchbase cluster to the Elasticsearch cluster, where the documents will get indexed, and it will be utilized for the full text search. You can find more information. We have a white paper on the Elasticsearch in our website. Okay, so let's demo the stuff we just learned. So before we start with the demo, let me set up for the demo. So let me explain the key concept of the document modeling, as well as how we build the index on the data. So let's say that we have three nodes, three objects for the game setup. We have player, monsters, and items. And the way the game works is player fights the monster, and monster dies, and it drops some items, which player collects and it owns it. It's very fairly simple game. In terms of document modeling, itself, the player document, it looks like this. We have ID, name of the player, and few other attributes. So this is how we model your document in JSON. We have the JSON type, ID, and other attributes. Similarly, we have items document which has ID and also some references to the reference to the owner ID, who owns this item. So we have this Dale 9887 who owns this item, and also the monster document, which is again which has again some ID and other attributes like the experience when killed and hit points and other stuff for the monster documents. So let's go back to the demo. Creating views is, if you come to the view page, you can see, as you can see there, we have the two options. We can create a development views and production views. In the development views, basically you create views here in the development views, and once they are ready to be pushed to the production, we publish them. So let me create a view, create a view called player. In this example, let's find out which player is winning. He has he's in which level basically. So let's say leaderboard. I have the script ready. So when you click on the edit, so this takes you to the page, the page where this is a pretty good editor kind of thing. So where it gives a sample data on the top we have a sample data in the side and also the metadata along for that particular document. The metadata is it has the ID of the document, the revision ID, which I mentioned earlier, will be utilized for the XDCR. We have expiration we can set for the document, and after the expiration, the document will get deleted. So we have other flags, and one important thing to watch is we have the type called JSON here. When you refresh this page, you can see the different it picks up the randomly different documents and shows up here. Let's put the function here. So what this function does is it takes the document and the meta information. Since we want to find out which player is winning, in this case, we check the condition if the JSON type is player, and we emit the level. So when you hit save and click on the show results, so it will basically in the development subset, what it does is the view created is only on subset of the data. So here it shows that Aaron 718 is at level 1, but it's still not across the data set. So I will demonstrate how to do that. So another thing we can do is in the same view, we have a filter result. If you want to do the descending operation, you can do that here. You can checkbox this. You can you have ability to do other stuff, like you can do the start by query on the start key, end key, on the start key of the document ID, end key of the document ID, on the key, or you can even turn on the reduce, or there's a stale parameter you can enable. So once you do this and hit show results, it basically shows the result in the descending order. Now we know that Tony 8714 is at level 15. So once you click on the full cluster data set, which will now, when you save this, here what it does is it's actually building the view and the index on the complete data set. So as you can see, it's building the index on the complete data set. In the meantime, we can take a look at from the development view. Basically, the view is already created. We know that it's been tested. Now we can publish this to the production. So in production view, we cannot make any changes because it has to be rebuilt in that case. So let's see in the production view, when we click on the show results, it's run across the entire data set. We do the descending operation again. Yeah, so now we know that Laila 3442 is the player. She's at the level 17. Then there are other 3 guys who are this level, and other 4 guys who are this level 17, and they are at the top level. So and as I mentioned, this is on the entire data set. So it's not only subset of the data set. Okay, in the interest of time, I'll quickly move to the next thing, which is the cross data center replication. So as I mentioned, we can easily set up a cross data center replication between the clusters. The way we do, I have already set up another cluster of 4 nodes. So it's as simple as adding a IP address from one node of that cluster. So for example, I pick IP address of one node from this cluster, go back to our source cluster, create the adding the cross data center application is a 2-step process. It's just creating a reference and as well as creating the replication streams. So we give the cluster name, and give the IP address of one node on the destination cluster, and hit save. So it creates the reference. Now the reference is already created. So now we create the replication streams. So we can choose the bucket. As I mentioned, we can it's a per bucket basis. So you can create the replication stream based on the bucket, which in this case we pick the default, and on the remote cluster. So we can have the same default name, or we can have a different name on the destination cluster, and it has to be, the bucket has to be existed on the destination cluster. So when we hit replicate, it will set the replication streams on the cluster. So when you quickly go to the server nodes and click one of the nodes, So if we go down to the XDCR docs per replicate, you can see we can click on the on this one. This stat shows that the replication docs to replicate has started. It's from the source cluster. We have around 80K the docs which are getting pushed to the destination cluster. Let's switch to the destination cluster and we click on one particular node. We can see docs to replicate here, docs per second. So here in this view, we can see that docs are incoming on this cluster. So it's as simple as like setting up the replication between the clusters and replicating the data is very simple. And also you can see that this cluster before was not having any traffic. Now there's a lot of activities. It's getting data from the source cluster. And once the data is synced between the source and destination, any mutation later on will be sent to the cluster, and it will be always in the sync. Okay, so let's get back to the presentation. Yeah, so part of the, as I mentioned, we provide a smart SDKs with Couchbase. We have the SDKs we have the official SDKs for Java, .NET, Ruby, and some of the other popular languages. And also we have a bunch of community contributed SDKs for the Node.js, Play, JRuby, and others. So now let's open up the floor for questions.
We have two questions about latency, so I would like to fold these into one. One's a question on read and write latency from the clusters. What kind of range are we talking, microseconds or milliseconds?
So from the presentation, if you remember, if the data is already in the memory, most of the operations are sub-milliseconds. So it will be very, very quick. So that's why we kind of recommend to size your cluster properly so that your active data set is in memory so that we have faster response time.
That's great. And then following up on that, what's the latency for using XDCR? Does that add any latency?
So what we are seeing is the XDCR, when in terms of like replicating the data, as you saw that once the data gets persisted to the disk, that's when it gets pushed to the other side. And the reason we do that is like we want to avoid if there's a particular document which got multiple frequently updated, we want to avoid we want to do the dedupe. In the sense, we don't want to send all the changes to the other cluster. We'll only when all the changes are done and it gets persisted to the disk, that's when we replicate to the other cluster. In terms of the replication latency, it's the network latency, but we have some tests, and some of the white papers on our blog will have that information.
Okay, great. A question about the best practices for backups. Do you recommend to do it in a specific node or an isolated node that might not be configured in the application?
The best practice would be to have another node which backs up all the data from the active nodes. And we have a tool called CV Backup, which is part of the Couchbase installation, which you can use. This is a command line tool which you can use for setting up the backup on the active nodes.
Great, thank you. Speaking about the cluster nodes, can you mix and match cluster nodes in terms of platforms? So could you, for instance, mix and match Windows and Linux nodes into the same cluster?
No, we don't support mix and match of different platform in the cluster.
Okay. One question from Luis. Is there a limit in the number of nodes in the cluster due to latency when you're replicating your data?
So we have the limit is, like, as I mentioned, we create 1024 partitions. That would be the limit. I mean, you can create 1024 nodes. But what we are seeing from the customers, they have created 60+ nodes, and in terms of they do well. They do good enough. I mean, they haven't seen any big issues with the 60+ nodes.
Okay, great. I believe at this time that's all the time we have for questions. For those folks who weren't able to get to your question, we'll follow up with you after the session. And just want to thank everyone for joining the webinar today. Really great questions, and we will send out the slides as well as a recording of the session later today or tomorrow. Thanks again for joining, and we hope to see you at a future webinar. Goodbye.
Thank you very much.